My name's Ben Mestel, and I'm the Deputy Director of the Isaac Newton Institute. The Director, David Wallace, is currently on a Eurostar train to Paris, which is why I'm standing in for him. I've only been Deputy Director for just over a month, so many of you will actually know much more about the Isaac Newton Institute than I do. But nevertheless, I'm delighted to welcome you here. I'm delighted to see such a great turnout. There are more than 100 people attending this workshop. Can I just say about the staff? The staff are here to help, and please don't hesitate to ask any of them if you need anything. The high Reynolds number turbulence program is a great program. I went to the Open for Business session a couple of weeks ago, and something came home to me there, because there was a guy from the Culham laboratory talking about nuclear fusion, and he said that if it weren't for turbulence, we already would have nuclear fusion. And that tells me that the work you're doing is immensely important. Can I say that we're very grateful for the organisers. The HRT programme has been fantastic, and I'd like to ask you to thank the organisers now with a brief applause. And without further ado, I'll hand you over to Julian Hunt, who's going to introduce the work.
Do we take off the fire? I'd like to use these two overhead. Good morning, colleagues and friends. I've enjoyed being at a number of Isaac Newton programs. We had a tremendous one in 1996 on mathematics of oceans and atmosphere. Mike Cullen, who's here from the Met Office, was a prominent member of that. Now, I'm here just to kick off with a few remarks, and some of my remarks are made from bruising encounters on the subject of climate with fellow politicians, and I'm partly going to blame the scientists for this bruising encounter. The important point really is that I think mathematics has a very strong role in geophysical fluid dynamics. Not, as it were, if I may say so, the people in the back room who just provide new methods of parameterization or new mathematical techniques for data analysis for the climate modelers, but in fact they are extremely important for providing the concepts and the words to explain what is going on. And if you're a politician, or you're hearing that the public debate on climate, it's the words. And the words, as Poincaré pointed out in Science and Method, which I hope you've all read, and George Batchelor said is the book that describes what applied mathematicians should do. He said that when you've done some clever science or mathematics or analysis, then you try to put it into words. It's only if you put it into words you've internalized it, and then you're in a position to then to go forward with another concept and further research. A little sort of a kind of wrinkle on that, made, in fact, an interesting conference on complex systems analysis and language last week in Bilbao, which I wasn't there but reporting on, is that you should also be trying to put it into words as you proceed. Poincaré said you should do it and you do it when you're finished. But actually, when you're getting stuck in a problem, I'm sure you do this, but you say, now what am I really trying to do at this point? And I think that this is part of what we should do. And when I had a little conversation with David Ritchell, who's a strong organizer of this, he pointed out that, as his own research shows, he's very interested in the questions of patterns and structures. There's quite a dialogue going on, I would say, in which the patterns and structure people are not winning at the moment, it seems to me, between those who want to do this approach and those who want to analyze, if I may say so, in a Lorentz Palmer way, of chaotic modes and saturation. Whereas if you're a sort of a deterministic fluid dynamicist, you like to look at real blobs. And just to remind you, one of the most significant climatic events that happened here in northwest Europe in the last few years was the very hot summer of 2003, which was not forecast by the numerical models and is still not forecast by the numerical models, but it was predicted by the statistical model of Mike Davey and Coleman, and Davey's in the back of the room. In May of that year, his model said it was going to be a very hot summer, and I pasted that onto my door of University College, put it in my notebook so you can tell it was a predicted event. And as he commented, though this is again not the standard Reading view of the world, and this is the Reading view of the world paper, there was a great big cold blob that forms off Greenland and moves down to Europe, and it persisted right through the summer, this extraordinary blob, which indeed Davy had commented about earlier as explaining this phenomenon. The other important feature, of course, about structures is that A, structures form, and B, they persist, and C, they have different behaviors either side of their boundaries. And this is a two-dimensional vortex in 2D flow produced by Voropayev at Arizona State University. And the extraordinary thing about this, I can't go, that's a longer talk, is this forms out of a much smaller vortex. So there's this important upscale transport that produces these big structures. So we need to, and of course we are very familiar now with Mike McIntyre here at Cambridge has worked on this, the interfaces dynamics of the ozone hole. But one of the most important points about these blocking events is that they may become much more common in future. The computations by Cazou at the at Surfax in France has shown this remarkable tendency to form these very large. If I've got my last, no, I haven't got this here. These tend to form much more commonly with climate change. The other important point is that we, as is now part of the general discussion of climate and weather, is the fact that we have these systems and we move between the systems. And at the moment, of course, we are in this very important period between the El Nino and the La Nina. And this is the reason why the IPCC graph that causes great confusion, which is the global average temperature over land and sea for the last 10 years, has remained static, and therefore you have whole books now written, like by Nigel Lawson, the former Chancellor of the Exchequer, calling an appeal to reason. You should read my review of that if you want. And the point really was that in the late 90s, we had a very strong El Nino, and I'm afraid some people who should have known better welcomed this as evidence that climate change was now here and strong. In fact, it was a very strong El Nino. And for the last 10 years, we've been having a cooling of the oceans, which has had this global effect. However, over the land areas of the world, the temperatures continue to rise. And it's very curious that the IPCC and politicians don't place this more strongly, but they do now, thanks to a question in Hansard in July of last year. I'm sure you all read Hansard regularly to keep yourselves up to date on critical scientific questions. I thought I would give you a familiar kind of overhead slide for those of you who know lectures. So one of the other really interesting phenomena is the patterns associated with orography. It's the orographic effects in the Antarctic Peninsula, which we've worked on with our colleagues in the British Antarctic Survey. That's the area of the world where the temperature has risen most rapidly, 3 degrees in 50 years, and it's been associated with a deflection of the stably stratified airflow caused by Coriolis. A similar phenomenon seems to be happening from time to time now over the Himalayas. As you know, the monsoon is a very recent phenomenon, only again for the last 20 million years, well, until the Himalayas, where they rose. But a couple of years ago, the airflow, instead of going around the Himalayas as it normally does and produces rain and RT in Assam, it stopped doing that and it moved the other way. There was the rain in the northwest of India, complete drought in Assam. These are the kind of patterns that we may expect to see in future. It's quite small changes in stratification. Those of you who study stratified flow over mountains would see what would happen. Of course, that is not possible to do in weather forecasts. But not to be negative, of course, there has been great improvement in medium range weather forecasts. This was a review in the American magazine Science, to show you not only that the accuracy has been increasing day 3, day 5, day 7, but the thickness of this line shows you the difference between northern hemisphere and southern hemisphere. and now we can measure those and predict those as accurately as each other because of satellites, which before we didn't have. So predictability is very important, and of course this is where our Isaac Newton program in '96 had interesting discussions between those who saw predictability in terms of the Lorentz, you could say Palmer view of the world, if I may write it like this, of chaos and modes and saturation versus structures. If you're a structural person, it's quite understandable to see that errors, if you displace a vortex in a shear flow, its errors will grow linearly. If, of course, you have displaced modes in a sort of modal pattern, you have exponential growth. It turns out that most storms and these forecasts are growing much more slowly than exponentially, and they grow approximately linearly. Though there's a large number of people who always plot these linear graphs on an exponential with a very small parameter lambda, but that's because you mustn't say anything against Mr. Lorentz. Actually, Lorentz's papers are very, very subtle on this matter, and he seemed to me to be very clear on this. Finally, I've just touched on extremes, and one of the interesting points, one of my former students looks after insurance in Lloyd's Register, and he still says it's very difficult to know whether ships sink because they have a set of random events of waves, and Professor Schreier is here from Kiel who knows that, or whether these are characteristic events, which of course we all think easier to understand and to deal with, and it's the same issue with weather. So when we're dealing with very extreme events like hurricanes, one of the extraordinary things about hurricanes is that we have these extremely thin shear layers, and those thin shear layers and how they form are one of the areas where classical and fluid dynamics, can make an important contribution. And the final point I want to make is that is to go back to my sort of earlier point that with mathematics and analysis and physics, it not only enables us to look at individual events and structures, it should give us new numerics if we're now going to focus on these extreme and very sharp events, but also it provides new uses and demands for data. You've probably never seen this picture before because it was always secret when I was at the Met Office, but now it's on the web and therefore it's not secret. But you can detect lightning and therefore strong convection all across the equator. You've probably never seen this picture before, but it's actually on the web now. By looking at lightning strikes, which you detect from military installations in the UK, Gibraltar and Cyprus, you can actually detect lightning over much of the world, and you can even detect them in South America, where they're used to tell when the Formula One racing drivers should change their tyres. That's an application that is not is lucrative but not serious. But the point being is that we all know this is, it's quite an interesting picture. You've never seen a picture before in which you can see these strong convective events coming from this. But the interesting point now is that this kind of knowledge with communications and satellites will enable, hopefully, this kind of information to be available for aviation and risk control in those parts of the world. And the final point I'd like to mention is that, with another funny story, is I took my 3-year-old grandson to the zoo at half term. And first of all, he said, did I know where I was going? And shouldn't I ask a few people? So he's as rude as his grandfather. But the important point was that you see at the zoo all these extraordinary projects of animals around the world. And then I went to a meeting at the zoo, and it turns out that now the animals, seals and so on, as they dive under the ocean, they have these small instruments attached to them. And now we're beginning to be able to see astonishing detail about exactly what's happening in these upper areas of the ocean, which in the past have only been sampled very spasmodically. So animals are coming to the aid of physics and mathematics. Thank you very much.
Can we make estimates of diapical mixing in the ocean, for example, animal tracks?